that is connected via what to this carbon? Double bond. What's it connected here with? Single bond. Single bond. So it's a carbon with 1, 2, 3, 4, 5, 6, 7, 8. Sorry, I didn't count 2 over here again. 8 electrons in its outermost shell. All right. So carbon, 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 carbon. Do you see why we abbreviate them? Because it would be a real pain to actually sketch them all out. So this is why we walk through that, is so you can actually look at this and be like, okay, I see. Like there's some rings, and the rings are just carbons all interconnected. Remember this ring? We sketched it earlier, right? It's a 5-sided carbon-to-carbon ring. And it's connected to a 6-sided carbon-to-carbon ring. So that's the only reason we go through it, is so you can look at this and have some familiarity with what the form means. So remember, the concept we're trying to illustrate is small pebbles making big biological waves. So these two molecules are hormones. And they're part of this group of hormones that are called sex hormones. And it turns out that this molecule, testosterone, if you expose a developing embryo to it during development, it becomes male. All right? If you don't expose it to it, and instead it just receives estradiol, this other molecule, it develops as female. So look at these two molecules, testosterone, estradiol. How different are they from each other? Oh. There we go. They're really similar, right? There's only a double bond here to the oxygen instead of a double bond within the ring, and then there's an extra carbon stuck onto it. That's the only difference. But your body during development magnifies this effect biologically and completely changes the way you develop. So teeny chemical difference, right? A couple atoms of difference is the difference between the embryo developing male and female in terms of its external genitalia. That's it. One last one of an example, okay? So I think this one doesn't reproduce very well, so I have to turn the lights off to see it. So this is a chart showing a bunch of different molecules. Take a look at them. You'll notice there's a new player, a new atom we haven't seen participating yet, a new element. Yes, I heard it. What is it? Nitrogen. So do you see the nitrogens here? So we have a 6-sided ring and a 5-sided ring with nitrogen. All of these molecules have that same basic structure. Then they're connected via a few carbons to another nitrogen of some orientation somewhere. And then the 6-sided ring either has some stuff stuck on it or doesn't. That's the only difference between all of these different molecules. You're familiar with this one here, whose name is tryptophan, and immediately in your head right now is a turkey, right? Because there's this false myth that you become sleepy upon eating Thanksgiving dinner because turkey is rich in tryptophan, and tryptophan makes you sleepy. My understanding, and I haven't actually looked into this, but my suspicion is that tryptophan is not unusually rich in turkey compared to any other protein. And the reason you're sleepy is because you ate too much. And when you eat too much, you become sleepy. So hopefully someday that myth will be put to bed. No pun intended. So tryptophan is an amino acid. And amino acids are these subunits that are used to build up proteins. So when you make a protein, and we'll talk all about proteins next time, you just add long, long chains of these different amino acids together. But one of the cool things that happens in your body is we take molecules like tryptophan and we modify them and use them for different purposes, which is one of the future things we're going to be talking about today or on Monday. So tryptophan can be slightly modified into this molecule, which is called serotonin. Have you guys heard of serotonin?
Yes.
Where is serotonin found? In your brain, right? It's one of the key neurotransmitters your brain uses for communication. A deficit of activity of serotonin is associated with depressive states. And so we take drugs if we suffer from depression, that elevate levels of serotonin in the brain. So, but all it is an amino acid that's had an OH stuck onto it and a few oxygens pruned off of it. That's it, all right? Just a regular old amino acid, something that your brain uses for communication. This is melatonin over here. Melatonin, you probably know, is like a sleep hormone, right? Have you heard of it? Some people take melatonin if they are jet lagged and things like that. Well, look at melatonin. It's basically like serotonin, all right, with like an extra carbon stuck on that oxygen. And now things are going to get really interesting. So this molecule here, psilocin, is a relative of a molecule psilocybin, which I suspect some of you know about. And psilocybin is a molecule that is found in magic mushrooms that makes you hallucinate if you eat it. So look at it, compare it to serotonin, compare it to tryptophan. Do you see it's just a few atoms difference? Supposedly sleepy after Thanksgiving. Hallucinating. Small chemical difference, big biological effect. And this one over here is bufotenin, which is secreted by toads of a certain type as a defense mechanism. And if you lick it, it makes you hallucinate. So again, it's just like a modified version of the same molecule. This is another one, those of you that are really hardcore and into this stuff will know about. It's called DMT, dimethyltryptamine. And DMTs are a category of drug that are super hallucinogenic. So basically, they're just like a regular old amino acid with a few atoms of difference and big biological consequence. So do you think you'd be able to come away from today being able to tell me of an example of like dissolves like and an example of small chemical difference and a big biological effect? Because that's kind of the goal of this discussion. Okay. I'm not advocating for you guys to go out and lick toads or eat magic mushrooms or find a DMT dealer or anything like that. But just pointing out, the chemistry is pretty simple.